All right, so yesterday we were working on this even function, odd function. So I just want to give you guys some examples, and also from those examples, I wish to show you some, some of those important algebraic forms, right? The algebraic forms of it. For example, for sine function, we have talked about that sine is an odd function, right? By the definition of odd function, right? By the definition of it. Okay, so let me bring back the definition of sine function, of odd function, right? Even odd function. Okay, I'm bringing back these definitions. When we read this definition, we must read it with, extreme care, attending to each word. That's what I try to show you guys, right? And its implication, right? For example, as an odd function, these examples I have given you, okay, we have completed these tables yesterday, is to demonstrate that for any x, right, for any x, any input, okay, where is x? It could be x, could be a, could be any symbol of your choice. F of negative x is negative of f of x. But what does this mean? What does this mean? Do you just simply, it's true, we can, if it's an odd function, we can take the negative sign out of it. If it's not, we cannot, right? If it's not, we cannot. But what does it mean? What is the meaning geometrically? So here so today we're going to start out with the, explanation, the geometric interpretation, right? The geometric interpretation. So what we try to interpret is, what is this meaning? What is the meaning of that? Okay, so I'm going to bring this over here. How do we understand, this picture, right? This picture. I think I can. All right. Knowing sine is an odd function. So we're illustrating this from this perspective of sine function, right? So I'm going to break this picture down. I'm going to break this picture down. Okay. So first I'm going to remove a couple of things. I'm going to remove the one of the purples. Negative pi over 4. So I'm going to remove that red. I'm going to remove that. Oops. Okay, so I'm going to bring this red back to okay, so this red should be yeah. Now it's right. Okay. First of all, yesterday we talked about for odd function, right? If f is an odd function, is a odd function. Okay. Help me. This should be A or N. That's a question with English grammar. Is it A or N?
I believe it's N.
It's N? Okay, thank you. So we're going to use N. All right. So when you look at this picture, what do you see, right? How is this related to the definition of odd function, right? So we're going to take the definition of odd function with us. And I want you guys to have your paper pencil with you, please. As an odd function, how is this picture related to the definition, right? Over here. It's an odd function, right? This, well, obviously we're using the sine curve to illustrate the concept, right? So we have two inputs. We have chat, thank you, and, right? And so if this is x, right? And the red is f of x. F of x. Okay, that's f of x. Okay, and this point has the coordinates of input, output. Okay, to be perfectly coordinated, I will use the blue. Okay, so these manipulation is a little bit tricky. Okay, so this is the input and that's the output, input, output. So that's the point on the curve. Now let's look at this piece, if this is x and this piece is a negative of x. Okay, that's how it's being created. And the purple is the algebraic form, right? The algebraic form is f of negative x. So ugly. And this point is a negative x, f of negative x. Under the circumstances. So because the assumption I made, this is x, this is negative x, and that's f of x, and these are the markings. So they're all connected based on the same assumption. We make that notation. Okay, they're consistent because each point is input output. This point is input output. Do you guys follow me? Okay. Or I'm waiting for you guys to write it down. I'm waiting for you guys to write it down. Are you done? In this example, I intentionally put the x on the negative side. So negative x actually is on the positive side because the opposite of negative is positive. The opposite of positive is negative. You guys follow me? Okay, so I'm going to give you another scenario. Clean this up. Okay, the next scenario is I'm going to call this guy x. Could I do that? Of course I can. Right? I can call this guy x. And what would this be? And that would be negative x. Right? Because they're opposite. And how about this point? This point will be x. The purple, f of x. Okay, so f of x is this much. And on this point, however, okay, still input output. The input is negative x. The output is f of what? Negative x. Do you guys see the consistency? But there's also variation depending on how the variables are introduced. If you have a relationship in the odd function situation, the picture I constructed here is to illustrate this piece, okay? We're not finished yet. We're not finished yet. Now, what is the negative of the red? Right, this is the red. What's the negative of the red? Can you draw it? The opposite of red, is gonna be this guy. You just flip over, right? So this is the red. The opposite of red is the purple. And these two purples are the same thing. If this red is f of a negative x, what will be the purple? How would you express the purple algebraically? We can draw it easily, but what is the algebraic expression? Well, the red is f of a negative x. Therefore, the opposite of the red is going to be, you put a negative sign in front of it, it's going to be f of a negative of the red. So this is the red. The opposite of red, you put a negative sign in front of it, but except this time it's vertical. Okay, input is horizontal, output is vertical. And by this time, this purple is going to be the same as this purple. You follow me? Therefore, this guy is the same as f of x, which is here. So these two quantities are the same. Do you guys understand that, illustration? Do you guys understand? Similarly, this piece of purple, if I flip over, what do I get? Well, the purple flip over, you get the red. And if you flip this purple over, you're going to get red as well, right? You're going to just get a red over here, right? For that input. And this purple flip over, you get the red. And how do you express this red? This red is the opposite of the purple f of x. Therefore, that piece is equals to what? If you are to express it, it's going to be negative of f of x. This is the f of x. The opposite of f of x, you put a negative sign in front of it. And this red is the same as that red. You follow me? So these two red, because this piece is f of a negative x, according to our notation, and this piece is negative of f of x, and these two are equal. I shouldn't be writing it this way. This will be confusing for you. So I'm going to write it here. So f of negative x is equals to negative of f of x. Negative sign in front of it. Are you guys with me? Do you guys understand? So one is the algebraic expression and the other one is the graphic representation. You have to be able to do both, especially you have to understand, this transition back and forth between algebraic and a graph. If you understand this process, then you understand a lot of things. Any questions? So the meaning of this piece, okay, there are actually two forms for it. The two forms are equivalent. One of them is here. We just show you, right? We just show you f of x, negative f of x, the red, and this red is the same as this one, which is f of negative x. That's the feature of an odd function. And the other form is that you put a negative sign in front of this guy, the red, you flip over, and the two purples are the same. okay? But from this algebraic form, if you multiply both sides by -1, you get exactly this form over here. You guys follow me? If you multiply this piece on both sides by -1, you will get exactly this piece on the top. You guys follow me? Yeah? So now I'm going to clean up and write these forms with better notation, with better notation. So for odd function, what it means, for odd function, what it means is that, what am I doing here? Okay, for the odd function, what it means that this piece, okay, meaning f of x, okay, so whenever the inputs are opposite their respective outputs. Okay, what are their respective outputs, right? If inputs are x and a negative x, their respective outputs, f of x and f of negative x, are opposites as well. We talked about this yesterday, right? Opposites. Okay, whenever the inputs are opposite, right? X and negative x is opposite. X could be positive. If x is positive, negative x will be negative. If x is negative, negative x will be positive. If the inputs are opposite, their respective outputs are opposites as well, implying that this blue, this purple and red are opposite. What does it mean they're opposite? If we put the negative sign in front of one, right? If I put a negative sign in front of one, we get the other. We get the other. We get the other. That's what it means opposite. Okay, or I can put a negative sign in front of this guy, and then they will be the same. So these are the two forms, algebraic forms. In particular, in our situation here with sine, in particular, okay, these are the general form, right? These general form apply to odd functions all over the world, all over the universe. But in particular, if I substitute f by sine, what will this form turn into? This form, these two forms will turn into what? If f is sine, f is sine, f is sine, f is sine. That's what it turned into. You guys see that? If f is a sine, it turned into this because sine is odd, right? And of course, you can actually remove this this parenthesis. You can remove that parenthesis. So these are the two algebraic forms we were explaining. In summary, if we go back to explain the nature of odd function on this sine curve, okay, so let's mark it again, right? Previously, we used a general function to mark odd function. What if we just mark it on sine, right? So now we can mark this as x. Okay, we can mark this as x. This is a negative x, right? And this piece, if this piece is x, and that piece is going to be sine x. This point is x, comma, sine x. Okay, input output. And this other point, because the input is a negative x relative to the x, negative x, and this purple is sine of what? Negative x. And that point is marked as input, output. Okay, now flip over the purple. Flip over the purple, this purple. We got this red. We got this red. Flip over this purple, we get this red. And the purple, which is this much, right? Sine of negative x. If we flip this purple over to the red, what do we get? We simply put a negative sign into the purple, which is and these two reds are the same. These two reds are the same. By the same token, if I flip over this piece of red over, I get the purple. And this red is sine x. So if I flip over, it becomes negative sine x, right? Because it's opposite. And these two purples are the same. So negative sine x is equal to sine of negative x. You guys follow me? Do you guys follow me? So one is the algebraic form, and the other one is the geometric interpretation. The digitized geometric interpretation. Any questions? Any questions? No, you got it? All right. So if you have any issues, you can watch this piece all over again, or we can talk about it again. If you watch it again, you don't understand, right? I think you just need to watch it over. I think my explanation, did I make any mistake here? Did I make any mistake here, Farouz? I hope not. I don't see anything, any mistake I've made, right?
I don't see anything.
Okay, thank you. So you just make sure you understand that all these symbols, right? And their geometric meaning of it, right? Why do I emphasize these? Because when you do transitions, reflectings, and all of these, you're gonna use these all the time. You're gonna use these all the time, okay? So I'm gonna clean up, okay? Did you guys write it down, take a picture and stuff? Okay, so I'm gonna clean this up. So let's look at cosine. Let's look at cosine. Yesterday, I given you guys homework, right? I give you guys homework of those 4 tables, right? Those 4 tables. Let's see, what are the 4 tables? Sine table, right? I give you the sine table. We cannot do all of it in class today, okay? I give you the sine table, cosine table, right? Sine table, cosine table. We just, we just summarize the sine. For the sine, you basically have these 2 forms. Okay, sine of, wait, come on. Sine of negative x is negative sine x. Okay, also sine of x is equals to negative of sine of negative x. Okay, that's what we just covered, right? That's what we just covered. And we primarily want you guys to show this piece. But once you get this piece, you just multiply both sides by negative sign, you get the other one, right? So that's not a big deal. So this exercise is for you to see that from specific form, observe the features, and these features is reflected everywhere on the sine curve. For example, you can continue this kind of drawing. You draw the blue, right? You can draw the blue like that. I'm gonna draw blue. This is x, right? And what will be the negative x, right? The negative x will be on the other side, right? And what are the output? The output, one will be red, and the other one would be purple. And this red and that purple, they're opposite. So this is true everywhere. This is true everywhere, okay? That's what it is, an odd function. In particular, of course, it is true. It is true for these, selected values I have given you on the table, right? It is true for all of these. Counterclockwise, clockwise, everywhere. That's the meaning of it. So did you guys work out the cosine? Do you have any questions? So how about for cosine? For cosine, the explanation is pretty straightforward. It's pretty straightforward. Okay. So I drew the picture with my other class. So I'm just going to borrow that picture and use it directly here, because it takes time to draw those pictures. Where did I put it? Right here. This is a cosine. Okay, this is a cosine curve. Okay, this is a cosine curve. So what does that mean? You guys have found, right? You have found out, right? Whenever the inputs are opposite, what happened to the output? The output are exactly the same. Geometrically, on the digitized, geometry situation, right? So whenever the inputs are opposite, right? These two inputs, this input, if I mark this as x, and that's going to be negative x. And that's a cosine curve. So this piece of red will be expressed as a cosine x. Okay, and that point over there, that point, how do you mark that point? That's going to be x comma cosine x. How about this other point? Well, this other point, because the way we constructed x, the inputs are opposite to each other. Therefore, this piece is a negative x. And how about this piece of red? That piece of red is going to be cosine. Okay, that piece is going to be, let me move this closer. It's going to be cosine of negative x. Okay, so this is the red. So these two red are the same height. So this point, the input is negative x. The output is a cosine of negative x. And these two pieces are equal, right? Horizontal, vertical. The two verticals are equal. They're equal. You follow me? So that's the feature of even function. And this is true everywhere. This is true everywhere. So suppose you say, oh, I'm going to have another input, right? This input is going to be x over here, right? And the opposite of x is going to be over there. And what are their respective output? Well, this is the output. and that's the output. Same. How do you mark them? Same way. So the x can be any number in the domain of cosine. So that's the meaning of even function. And if you fold this piece of, if you fold the curve above the y-axis, they're going to completely overlap. One side is, for the negative input side, and the other side is for the positive input side. But they have exactly the same output when the inputs are opposite. Makes sense? You guys follow? So this is the algebraic to visual. The algebraic to visual. Any questions so far? Are we good? Okay, so now shall we look at tangent? Okay, your first quiz will be, about this. You guys have a quiz coming up this week. Okay, the first quiz is coming today, either today or tomorrow morning. Okay, I will try to get it ready to available today. It's going to be about even odd functions. Okay, so next let's look at tangent. You get your tangent curve at your fingertips, don't you? You get your tangent curve at your fingertips. Oh, where's my, I copied what I did for the previous class. So I don't have to draw it all over again. So right here, tangent, right? So this is a cosine. This is a cosine. Let's look at the tangent. Tangent x, right? So we have this is the tangent curve, right? So tangent is also odd. So the scenario is the same. Right? So if you let's look at these algebraic forms. Let's look at the algebraic representation. So if this piece is x, okay, if this piece is x, right? If this piece is x, horizontal, and that piece is a negative x. The red is going to be tangent x. So that point is what? What is that point? It's x tangent x. Okay, x is the input. How about the other side? The other side, this x is so ugly. Okay, so this is a negative x. Okay, this is a negative x, and this is the tangent of what? That's going to be tangent of negative x, because the input is a negative x, right? These two has a relationship. We utilize that relationship. And how about the point? The point here is negative x, tangent of negative x. Okay, and they are opposite to each other. What does that mean? If I flip the purple over, it's going to be the same as the red. If I flip the red over, it will be the same as the purple. You guys follow me? The same story about odd function, always the same story. Okay, another odd function you can work with is x raised to the power 3. It's also the same story. Okay, now tangent of, so that will lead us to these two forms. One of the form is tangent of negative x. Okay, tangent of negative x is the same as the opposite. Okay, the opposite of tangent x. Right, because if you flip this over, tangent negative x, if you flip the red over, you're gonna get the purple. If you flip the purple over, you're gonna get the red. Okay, so the next expression would be tangent x is going to be, right, tangent x. This piece is about to flip over the purple. Flip over the purple. What is the purple? The purple is tangent of negative x. Flip the purple over, you need to put a negative sign in front of it. And there you go. So these are the two forms. These are the two forms in algebraic form. You guys get it? All right. So how about secant, cosecant? Okay, so I want you guys to think about it. Did you guys write it down, all of these things? Okay, we're not going to do cotangent. We're gonna work on this, and we're gonna put a summary here. We're gonna put a summary here. So let's summarize. Okay, it's time to move on. It's time to move on. We have spent enough time on even odd function. So if you guys have any questions, please don't hesitate. But we're gonna summarize and we're gonna move forward. Okay, summarize. We're gonna move forward. Summary. Okay, I'm gonna put a few more columns here. Okay, in terms of the even odd features, right? The even odd features, the geometry and the algebraic. Sine x, we know is odd, right? It's odd. And where it is odd, well, we should be aware of its domain. Okay, we should be aware of its domain, right? You can also attach the picture to it. Right, we can also attach the picture to it. Maybe we should attach the picture to it. Okay, so let me redo the picture. Okay, sine x domain. I'm just going to do it slightly differently from my other class. Okay, so use this opportunity to review. So domain. So when we talk about domain, even odd function, even odd is in the domain of the said function. So we must make sure we understand the domain of that function, right? We must understand the domain of this function. So here I'm going to attach some pictures we have done for these functions, right? This is the cosine. Put the cosine there, right? And we have our sine. This is our tangent. This is our tangent. Okay, how about sine? We did a sine. That's sine. We did sine. Right, these three typical ones. Make it a little narrower. Okay, you got some work to do because in this summary, you guys is going to participate. Okay, you guys are going to participate. Okay, so we understood these pictures, don't we? Do we have any questions? You should have questions. Okay, sine, cosine, tangent. Okay, cosine x, tangent x, right? Where are they even or odd? What is domain of sine? Everybody should know that, right? From negative infinity to positive infinity. And cosine, the same thing. So that is, so these features described on the picture is same all the time, okay? And the tangent, however, what's the domain for tangent? What's the domain for tangent? Hello? It's not about memorization, but do you know how to figure out? Riley, you about to say something?
Y does not equal 0. Did I get that backwards?
Y is not equal to 0. What is Y?
Um,
When we talk about domain, we're talking about what this can be. We can use
Oh.
domain is about input. What is the domain about the A?
oh, x cannot equal 0.
X cannot be 0.
Right.
You mean this? Which X? This X cannot be 0. How we go about to analyze that? Apparently, this picture tells you X can be 0, right? When X is 0, that Y is 0. The curve crosses 0, 0. So X equals 0. Obviously, it's not the right answer. What's the domain of tangent? Tangent is equal to sine over cosine, right? Right?
Right.
If tangent is sine over cosine, cosine is in the denominator, so cosine x cannot be 0, right?
Right.
What will cause cosine equal to 0? What will cause cosine equal to 0? What are these points? What are these points that cause cosine equal to 0? Look at the unit circle. Look at the unit circle.
When x is equal to 0. When
Cosine 0 is 1.
pi over 2. Yeah, increments of, right, pi over 2.
Okay, pi over 2 it cannot be. Is there any more? Is there any more?
3 pi over 2.
3 pi over 2 it cannot be. And the list go on. What else?
5 pi over 2.
And so you're going to keep the list go on like that. Do we have a pattern for it? Where's my unit circle? I'm going to find my unit circle. Keep going. Keep going.
So 7 pi over 2. 9 pi over 2. 11
Very
pi over
good.
2.
All right. Is there any pattern for it? Because as you enumerate it, it sounds like you understand that there are infinite number of them, right? How can you finish enumerating infinite number of numbers that cannot be in the domain? So what causes cosine equal to 0? What number causes cosine equal 0? What causes cosine 0? Because cosine x is in the denominator. If cosine equals 0, those input cannot be in the domain. So what are the zeros? What are the red number that's equal to 0 on this unit circle?
Pi over 2.
Pi over 2, 3 pi over 2, positive, negative, and so on and so forth, right? So it's what? It's odd number multiples of pi over 2. Can you guys
Yes.
write that down? Write it down. Speak it. Speak it.
Odd number multiples, pi over 2.
Odd number multiples of pi over 2.
So,
You remember I said that.
so that means the domain of tangent cannot.
Domain
equal-
can be any real number but odd number multiples of pi over 2. Can you speak it? Please speak it.
The domain for tangent can be any real number.
It's not about memorization, you guys. You need to understand. Because when you put those in these terms, when you speak it, you will truly understand. Otherwise, there's no understanding. I teach for understanding. Do you guys understand that? Right? As we enumerated, this is the answer your professor in calculus is expected of you. Okay? Odd number multiples of pi over 2. When you say increment of pi over 2, what kind of increment of pi over 2? How do you increase or decrease it? This answer is ambiguous because pi is an increment of pi over 2, right? Double pi over 2 is pi, but pi is in the domain of tangent. So that description, increment of pi over 2, is not accurate. The precise description is odd number multiples of pi over 2. Could you guys please write it down? We have said this many, many times. If that phrase doesn't help you to understand, what phrase will help us to understand it? Tell me, can you modify that phrase so that you understand it and you can address it? You can speak it all over again. You can speak it using other words. That's not a problem. Because we need to identify all the numbers that cannot be or can be, to be or not to be. Then these descriptions have to be complete. Someone wants to say something, go ahead.
Professor, I understand the odd number part and like the pi over 2, but I was wondering how you get the 2k plus 1. I know if you plug in a number, you'll get an odd one for that.
You always get odd number, don't you?
Yeah, but how do you
Let
get
k
the
run
2k
over from
plus 1?
0, 1 to plus 1 minus 1 plus 2 minus 2. You let k to be any integer. Don't you always get integer? So if this part you don't understand, let's do it. Why 2k plus 1 is a representation of all the possible odd numbers? Is that the question? Is
No,
that
I was
what
just wondering where you got the 2k plus 1. I already plugged it in, like if you do -3.
2k is always even, is that right?
Yeah.
2 times an integer is always even number, yes?
Yes.
An even number add 1 is always odd, yes?
Mm-hmm.
So does that make sense?
Yeah.
So do you guys want me to go over 2k plus 1? I would be happy to 2k plus 1 because I found you guys to get kind of, because what you show me, you don't understand it. And let's go make it, let's understand it. Okay, so let's look at 2k plus 1. What is the meaning of it? What is the meaning of it? Right, what's the meaning of 2k plus 1? While k is any integer. Here we say k is any integer. Do you hear that? K is any integer. What are any integer? What are any integer? What are any integer? Think arbitrary. 0 is an integer, right? Plus 1 minus 1 is integer. Plus 2, positive 2, negative 2 is integer. And the list go on.
Infinity.
Yes? If you plug in any one of these numbers into 2k plus 1, do you get odd numbers always?
Yes.
Absolutely. Are you going to miss any odd number? No. Are you gonna miss one? Say, give me an odd number. Give me an odd number. I can tell you, I can find a k, so I can represent that integer by 2k plus 1. Give me an arbitrary integer. So this question has a two-sided story. Okay, this has a two-sided story. Number one, it should represent any odd integer. Okay, so there's a two-sided story. The first side is that given an odd number, arbitrarily, okay, 2k plus 1 can represent it. Okay, given an odd integer, there exists, I'm not sure this is, there exists an k such that 2k plus 1 is the same as the given integer. Okay, the other side of the story is that for any integer k, right, 2k plus 1 is odd. So this is the two sides of the story. So now let's use some examples. Okay, I'm not trying to prove this. Let's just look at some examples. Okay, just look at some examples. Just now, Riley just talk about pi over, 3 pi over 3, 3 pi over 2, 5 pi over 2, 7 pi over 2, right? So let's pick up those odd numbers, 5, 7, 9, etc., right? Say I give you integer 5. Can I write 5 in the form of 2k plus 1? Right, that's the number Riley was
Yes.
talking about.
Where
Can I write
k
5 in terms? So you go ahead.
where k equals 2.
That's right. 2 times 2 plus 1 is 5. Isn't this in the form of 2k plus 1? Do you guys see that? K equals to 2. 7. How can you represent 7 in the form of 2k plus 1? It's 2 times 3 plus 1, right? Is that a 2k plus 1? Is that in the form of 2k plus 1? Where k equals to 3? How about negative 13? How do you represent negative 13? Well, 2k plus 1, I don't know what it is. I can solve for k, right? I can solve for k, could I? Can you guys solve for k from here? What do you get for k? Can you solve this equation for me? What do you get for k? What do you get for k? You subtract 1 on both sides. What do you get? Yes, you can write 2k minus 1. Arbitrary, 255. All right, let's go. Let's do it. Okay, we're going to do 255. Can we write 2k minus 1? Absolutely. Okay. 2 times negative 7, right? So Christopher got k equals to negative 7. Is that what you guys got? He's absolutely right. When k equals to negative 7, right? How about 225, 255, 255? Wait, 255. Can I represent 255? Well, I don't know what K is, but I can set up an equation and solve it. What do we get for K? 2K equals to 254, right? And what does K equal to? What does K equal to?
Was there a typo?
Did I have a typo? Oh, 254, yeah, thank you. What does K equal to? Come on, you guys can do this, can you?
127.
127, excellent. So can we represent, so if we keep going, right? Do you see that every odd number can be represented in the form of 2K plus 1? Yes? Yeah? Yes? No? You got it? But what if I use the form of 2K minus 1? You just get a different K, right? It still works, right?
Wouldn't the K be 128?
That's right. That's it. So it doesn't matter you use 2K plus 1 or 2K minus 1. A lot of the textbook use a 2K plus 1, and some textbook use 2K minus 1. I hope in this process you have learned to appreciate some of the mathematical forms, right? Yes? Yeah, do you guys see that I'm giving you some of the, and for any integer 2K plus 1 is odd, that's easy, right? Because 2 times a number, 2 times an integer, this is always even. And any even number plus 1 is always odd. Any even number minus 1 is also odd. That's why 2K minus 1 is also, it's okay too. Most of the textbook using 2K plus 1. Some textbook using 2K minus 1. Doesn't make any difference. It doesn't make any difference because the bottom line is that we want to represent all the possible odd numbers. Yeah, any other questions? Odd number multiples. So now if I ask you how to determine the domain for tangent, can you guys say that domain with a little bit, of course, I expect you to think about it. Can you say that fluently now? Can you? Can we?
Yes.
Good. Thank you for bringing up the question. Thank you for bringing up the question, right? You have to just let a K runs in your head. 0 plus 1 minus 1 plus 2 minus 2 plus 3 minus 3. And it has to represent all the possible odd numbers without missing one. No odd number should be missing. It has to be completely thorough. That's why your professor expects this answer, because this answer is the most thorough and the simplest. You don't have to tell your professor, oh, negative 3 pi over 2, 3 pi over 2, because you're never going to be able to run that list completely. Do you guys understand that? So now do you agree this is the best answer possible? Do you agree? That's the best answer possible. The simplest, the sleekest, the cleanest, the most complete, without one missing, all included. All right. All right, so in that domain, what is odd even situation? Well, we know that sine is odd, right? 125%. Do 125%, so this table is just a little bit too big. So this function means what? It's odd, right? So let me put odd here. And cosine, we know that it's even, right? Let's get to the algebraic form. Let's get to the algebraic form. What is the algebraic form? If you tell me, oh, sine is odd and you don't know how to use it, what's the use of it? No use, right? Chapter 5, calculus 1 will be addressing even number, even function, odd function when they talk about the integration properties, right? So for that reason, I'm addressing this and spending so much time. Actually, I have never spent so much time on even odd in my pre-calculus classes. And I hope this is helpful. I hope this is helpful. The algebraic form of sine, right? Because it's an odd function, we just talked about it. Sine of negative x is equal to negative sine x. And there's another form, sine x equals to negative of sine of negative x. Either form may be used. Okay, the first one is most popular. But these two forms are really identical. They're really the same thing, okay? That's why people prefer the one on the left. But you can easily get the right. And we spend some time to explain to you the meaning of putting negative sign at different places. Okay, at different places. Cosine. Cosine is pretty straightforward because cosine is even, right? So on the one hand, we have the description saying that, you know, for odd function, for whenever the inputs are opposite to each other, their respective outputs are opposite. Well, what is the algebraic form? You say the words for understanding, but you have to be able to do the algebra to get the points, don't you? Right? So you need to know both. You need to know both. Okay. Excuse me. How about tangent? Is tangent even or odd? We know it's odd, right? So let's look at it algebraically if we can derive it if it's odd. So you start with that, right? So then you have sine of negative x over cosine of negative x, right? You guys see that clearly? Is that big enough for you guys to see? You guys see that? Are you guys writing it down on your paper pencil?
Yes.
Thank you. So sine of negative x is what? Is a negative of sine x. Cosine of negative x is the same as cosine x because sine is odd, cosine is even. So this will be equals to what? Equals to negative of tangent x. So this is the algebraic proof of tangent is odd. Okay. And now we have questions. How about cotangent, cosecant, secant? Take a cotangent, for example. Take cotangent, for example. Cotangent x equals to what? Cosine x over sine x. We haven't done cotangent, okay? Now I want you guys to put on your thinking cap. From what we have done, okay? Work on your paper pencil. tell me, is a cotangent even or odd or neither? 5 minutes. 5 minutes. 5 minutes. Shall we do breakout rooms? And you also think about cosecant and secant. Are they even, odd, or neither? Or neither?
I'm ready, Professor, if you want to create breakout room.
Okay, I'm going to create the breakout rooms. Okay. Voluntarily. Okay, you can choose to work here, or you see all of these are derived from where? ARD. ARD. You don't need to go elsewhere. You don't need to memorize much. They're all from ARD. Do you agree with me? So how about for cotangent? How about for cotangent? Secant, cosecant. I'm going to give you some hint. Okay, so you need to work on secant, cosecant, cotangent. Okay, you don't need to get the picture. Don't need to get the picture. Okay, don't worry about the picture. Just on domain and even odd property. Domain, even odd. Okay, so only domain, even odd. All right, guys. For those of you who stayed with me, right? Don't worry about the curve. What will be the domain for cotangent? Well, then you see that sine cannot be 0, right? What makes sine equal 0? Any number that makes sine equal 0, which is a k pi, right? We can tell that from the unit circle, right? What to make you know, sine equals 0? So where the blue number 0, right? Where the blue number 0? The blue 0 are terminal, either the standard position or the pi position. So the multiples of pi, right? The multiples of pi. So in that domain, and the k, of course, is any integer. Is any integer, right? And cotangent, in terms of even odd, so you just have to start with the cotangent of a negative x equals to cotangent of negative x will be equals to cosine of negative x over sine of negative x. Okay, and then we're going to use the even odd property for cosine with, you know, cosine of negative x is the same as the cosine x. And the sine of negative x is a negative sine x. So this way you get a negative of cotangent of x. So cotangent is odd. Cotangent is odd. How about secant, cosecant? I put them next to cosine and sine. This is basically a hint. Because cosecant is 1 over sine. Okay, secant is 1 over cosine. Right? So in this case, the denominator cannot be 0. Denominator is sine. What else has a denominator equal sine? Cotangent. Therefore, the domain of cotangent is the same as cosecant. And this denominator is cosine. Therefore, the domain is going to be the same as tangent. Right? Okay. And then even odd. Well, if sine is odd, cosecant is odd. Right? All you have to do is use a cosecant of negative x. So do you guys see that? Cosecant of negative x is equals to negative of cosecant x. And secant, right? Cosine is even, therefore secant is what? Secant is what? Secant is even. Okay, so I'm going to close the rooms. I trust everybody already got it. Okay, so secant of negative x is secant x. All right, and I apologize for this mess. Sometimes it's all right. So that's it. That's it. Okay, we get a domain. You can see the relationship, right? You can see the relationship. So let me put it this way. Okay, you can put the pictures in, but you really don't need to see the picture. What I would do is I'm going to make this table just a little bit smaller. Okay, I'm just going to put it on top. Okay, I'm going to remove the last row, which is not used. I'm also going to remove this row. Okay, you already have that. So this will make it a little bit condensed, just on the even odd, Okay, so this would be the summary of the even odd properties. The even odd properties of, you can see sine is odd, cosecant is odd, cosine is even, secant is odd, tangent is odd, cotangent is odd as well. Okay, so I'm missing one of the columns. Okay, so I missed the tangent here. Yeah. I'm missing the cotangent. So right here, and my cotangent, it's odd. All right, so welcome back from the breakout rooms. How is our study? How is our study?
We are catching up, Professor. It
Very
takes-
good. So I basically went over, I'm sure you probably have done the same thing, is that because the relationship between cosecant and sine is odd, therefore cosecant is odd. Right, that's true. Cosine is even, therefore secant is odd. They're just, their domains are different. Their domains are different. And domain-wise, I want you guys to look at these, right? You can see that cosecant is 1 over sine. Cotangent is a cosine over sine, right? They both have the same denominator. So they have the same domain. Secant is 1 over cosine. Tangent is a sine over cosine. They have the same denominator. Therefore, they have the same domain. You guys follow me? Yeah? All right, I think we can put a closure to this even odd function discussion. Do you guys have any questions? Yes? Do you guys have any questions regarding this? Do the homework, okay? The homework I assigned yesterday. Okay? This will get you guys familiar, to review those contents. Remember, you're doing 5 classes in one. Sometimes you just have to do, you do the trig questions, but you're also reviewing the, pre-algebra, elementary algebra stuff. That's the nature of this course. That's what you sign up for. You have to work super hard. There's so much content. I'm sorry, I don't want to tell you otherwise. I don't want to tell you, oh, it's very easy, you get it. It's not easy. It takes a lot of work. It takes a lot of work to get it. Okay, I'm not going to tell you it's going to take you no time to get it. And I'll be lying to you if I do that. Can I see the columns? Can you guys see these? Is that too small, too big? It's a little too small. Let me do some rearrangement. Let me do some rearrangement. I do the vertical with the other class, and I am doing the horizontal with this class. I don't know which one is better. Which one is better?
I guess the vertical is better, Professor. So we can
Vertical
see
seems
everything.
better, right?
Yes.
So cosecant, cosine, sine, tangent, cotangent, right? I put them on pairs. And for sine, that's the algebraic cosecant cosine even secant even tangent cotangent. Okay, domain. I have no intention to put this together here for you to memorize. If you do just try to memorize, you have defeat the whole purpose. Okay. My lecture, I intended for you to watch it over and over. If you do that, you're gonna ace every quiz. My quiz questions, let me tell you, my quiz questions is not from any textbook. I made them up. Okay. And I made them according to my lectures. Do you understand? So if you watch my lectures 3-5 times, you're gonna ace every quiz. Because I want you guys to get to the bottom of these questions so that you can be free. You can be free at last.
Professor, I see this summary of even odd function table could be memorized, or I mean, could be learned or practiced like multiplication table if you are interested.
Yeah.
Practice, practice, practice.
You have to do it. You have to do it by your own hands. Okay. If you simply memorize these tables, I tell you, you're gonna hate me because there are too many of them. It's the process of getting to the summary. It's the process of getting to the summary. And it's that process, right? We keep talking about it, right? It's a process that's valuable, not not this result. If you only remember the result, you want to take that shortcut. I have to tell you, I'm sorry, that shortcut is not meant to be taken. If you try to memorize these details, you are going to be so overwhelmed. Okay, and you're going to be so confused. You have to understand the process to get to the table. Okay, so in this process, what have I done? You look, you see how I made the table, right? I first do this, did the sine cosine, right? And then I realized the relationship between sine and cosecant. One is odd, the other one is odd. This is going to be even. And there's the proof, right? And you need to do this independently. I assure you, every one of my lecture is worth you to watch it at least 3 times. I'm not boasting about myself. I'm talking about the contents. The contents. Okay, if you are that student, you want to make, do well in this class and do well in the next class, you watch my lecture at least 3 times. Each one of them. And then you will ace every quiz. You ace the course, I guarantee. And you will ace your next class. When you watch it, okay, all those details we have spent time on. A lot, I assure you, a lot of those details has not been covered by any textbook. None. A lot of the contents I covered here has not been covered by any text. We can ask for Ruth. Right, Faris? You don't have to agree with me.
I just want to announce, Professor, I agree with you 100%. Beside that, today I'm gonna be in Math Study Center from 3 to 6. It's just voluntary basis. If
Right.
anybody want to practice more. Yesterday, a couple of your students stopped by and did feel good about this odd even function. I encourage a student take advantage of that.
Wonderful. I'm so glad to hear that. Okay. All I'm trying to do that we did all of these groundwork. Okay. All of these groundwork we're doing here. Okay. I want you guys to be patient first. Patient. In the end, you'll be free. Free at last. If you want that. But freedom is not free. Freedom is not free. Okay. I want to bring you guys to the state of freedom, but that freedom is not free. It's not free from effort. Okay. All right. So when you study, please, okay, any tiny little questions, you must get it to me. If I cannot solve it, I will get help. I will get help. But you must let me know. For example, today the discussion we did 2k plus 1. If you didn't bring up, I wouldn't think that was an issue. And now I realize, oh, that's an issue. Let's go. Let's do it. Right? And after we resolve, how do you feel? You feel better? You feel better understand the material or not? Riley? Do you feel you have better understand that now?
Yes, I can articulate it better.
That's right. That's what you do. You don't want to overlook any tiny little question. You just need to get it to me. I'm here for you. I'm here for you. Okay? And you need to watch these details. Watch these details. I might have missed things. I'm sure I missed a lot of things. Because we can't put everything together all at once. Right? So you can see the making of the table. The making of the table. The making of the table is logical. Why do I put a sine with cosecant together? Why do I put a cosine with secant together? Why do I put tangent and cotangent together? Why in the end, most of the cases, the function you work with is just this one, this one, this one. Most of the time. Occasionally, you have to deal with the cosecant, secant, and cotangent. Yes, you do. I can't say, oh, you only do sine, cosine, tangent, and forget about the other three. No, I cannot tell you that. Because you're going to come back and to tell me, hey, Professor Wang, you know, that was not right. We have to deal with the secant and cotangent and all that sort of thing. You know, I'm sorry, I can't tell you that. Okay, but anyway, I think it was a very good class, but I still want to give you an introduction to inverse function before the end of the class today. So any question, every question, so please bring them to me, okay? If you want to do well, you know, you want to, you know, and today during my office hours, there's one student, he visited my office hours, and we went over some stuff about secant and cosecant. Remember, I have given you some study guide for about secant and cosecant to do the, you know, domain range and you know, the calculus perks and stuff. And that student came over and I recorded that piece of office hour time. So I will make it available to you after the recording is maybe later today, later tonight, okay? So I will make that recording. So all the recordings, they're available in modules. So please check them daily. Okay. I put them in the order of from top to bottom. You have to go through the weeks. Okay. I want you to go through the weeks, and because maybe one day you say, oh, realize I need to read this, I need to read that, I need to review this, and I review that. Excuse me. This week, I'm going to actually give you a review quiz on exponential and logarithm. So you should expect a quiz today. And you also should expect another, you may have 3 quizzes today, this week. I'm sorry, I might give you 3 quizzes today, okay? But study, 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 okay? We are very fortunate we have Farouz, and you are always welcome to see me. So now we have 1 minute, so let's just do it tomorrow then. Do you have any questions? I wish to tell you, I enjoy teaching you guys, or enjoy helping you guys. Okay, no question is too small. Okay, and well, something else may come up later on sometime in this semester. But I want you to always remember, I'm always here for you. I'm always here for you. Okay. So I will see you guys tomorrow. So tomorrow we're going to start talking about the remaining 4 inverse functions. Tomorrow we're going to start that. I hope we will finish this week, but expect 3 quizzes this week. Okay. I'm sorry, I cannot make it any shorter. And Farouz is announcing his office time, and keep up with your good work. Okay, all the questions are welcome, and they are all great questions. And I will see you guys tomorrow. Thank you so much for your participation. And I'm always ready to jump into topics that you want me to explain at any time.
Thank you, Professor. See you tomorrow.
Thank you. I'll see you tomorrow.
Thanks for the lecture, Professor.
Of course, anytime. Have a great day.